Introducing CAROM, Vehicle Localization and Traffic Scene Reconstruction from Monocular Cameras on Road Infrastructures. CAROM means Cars on the Map. It is a framework to track and localize vehicles using monocular traffic monitoring cameras on road infrastructures. The vehicle localization results can be stored in files or in a database as data records. Using these results, a traffic scene can be reconstructed and replayed on the map. The vehicle tracking pipeline contains several steps. First, we run a detector to obtain the instance segmentation masks and 2D bounding boxes. Next, we calculate the apparent motion of the vehicles through sparse optical flow vectors for each adjacent video frame pair. Meanwhile, this also allows us to associate detected vehicle instances on the image across frames. Then, we use the vehicle motion segmentation mask and camera parameters to compute the vehicle's 3D bounding boxes. After that, we transform the vehicle pose from the 2D image to the 3D space and run a common filter to smooth the vehicle states. Finally, we visualize the vehicle locations and dimensions on the map. Here is an example. We deployed 4 cameras in the 4 directions of an intersection. The satellite map and the videos from the 4 cameras are on the left side. The detected instance segmentation masks and computed 3D bounding boxes are on the right side. We can see the location of vehicles can be correctly captured most of the time. Here are the detailed results on the intersection eastbound. We can see this method can still work with slight occlusion. Here are the detailed results on the intersection southbound. Here are the detailed results on the intersection westbound. Here are the detailed results on the intersection northbound. Here are the detailed results at a different site on the local road segment. In this place, the vehicle speed is significantly faster. Here is a comparison of the localization results from an infrastructure-based camera on the left side and the localization results from a drone-based camera on the right side. The location results can also be replayed on a 3D map. There are 2 fundamental problems for vehicle localization using monocular cameras. One of them is vehicle pose estimation. We use the sparse optical flow vectors to estimate the vehicle orientation by assuming that the vehicle only moves forward. If the sparse optical flow vectors are all close to 0, we apply a deep neural network to derive its orientation on the 2D image. This neural network is trained on image patches of detected vehicle objects with significant observable motion. Then, we use the camera projective geometry and the tangent lines from the vanishing points and the vehicle segmentation mask to calculate the vehicle's 3D bounding box. Many improvements are made in the implementation details to accommodate various view angles and non-boxy shapes of vehicles. The other fundamental problem is the transformation of locations from the 2D image to the 3D world. Here, we set up the 3D world reference frame using the satellite map. Then, We determine the transformation using a set of manually labeled point correspondences. Typically, the ground is close to flat, and the transformation is planar homography between the 2D image and the XOY plane of the 3D world. The actual distance between 2 points on the image can also be recovered by this transformation, because the map is to scale. Since the camera is not moving, this step only needs to be done once after the camera is installed on the road infrastructure. If the road segment is far from flat, we can also fly a drone and construct the 3D map using simultaneous localization and mapping software. Once the location, orientation, and dimension of a vehicle are determined in the 3D space, we run a tracking by detection procedure on each video frame. We also use a common filter to smooth the vehicle trajectory and estimate the speed. To quantitatively evaluate the localization accuracy, we drove a test vehicle with a differential GPS device as a reference measurement method in the intersection northbound. Here is the comparison of location measurements between the infrastructure-based camera and the GPS. We can see the differences are small and they are mainly in the camera pointing direction. We also evaluated the localization accuracy of the infrastructure-based camera using a drone-based camera as a reference at a different site for multiple vehicles. On average, the location difference between our camera measurements and the reference measurements is around 1.5 meters to 2 meters within the coverage of about 120 meters. Accurate vehicle localization can support many downstream applications. For example, given the videos from the 4 cameras pointing to the 4 directions of an intersection, the same vehicle can be seen from multiple different view angles. With the vehicle location obtained from each monocular camera, we can reconstruct the vehicle shape from its segmentation masks. The vehicle shape is represented as a 3D voxel model. It can be further refined by fitting the reconstructed shape on the prior model, which is a deformable 3D model computed from multiple 3D CAD models of real-world vehicles. Here are some of the reconstruction results. Although not all vehicles can be reconstructed due to occasional occlusion and restricted camera angles, these pairs of 2D images and 3D shapes enable further development of deep learning-based methods to reconstruct the 3D vehicle shape from a single image. In another application example, we can use the vehicle location results and the map semantic information to analyze driving safety. In this case, the map is semantically segmented into multiple regions. At each video frame, a vehicle is associated with a map region, and we use this information to detect vehicle interactions and dangerous driving behaviors, such as minimum safety distance violation or traffic rule violation. Moreover, we are also implementing a system to calculate the locations of vehicles in real time and stream these results to nearby automated vehicles. Because these cameras are usually mounted at a high position with large coverage, these vehicle localization results are a good supplement to the limited line of sight perception capability of automated vehicles on the ground. Thank you for watching. More demo videos are available at our GitHub repository. This project is sponsored by the Institute of Automated Mobility, the Arizona Commerce Authority, and Arizona State Government.